Okay, moving on to chapter 9, differentiation. First thing to note, throughout this chapter you will be using radians whenever differentiating trig functions. In fact, in any calculus questions, we are going to use radians in both differentiation and integration. So as a reminder from first principles, we've got the derivative or the gradient function or differentiated f of x. You're going to use this formula, which is quoted in the formula booklet. So let me just remind you where it comes from. So remember, this is the gradient function. So what you are looking for is finding the gradient of the function at a point A, at a point with a with the x coordinate. In this case, we called it x. So the idea is to just move a tiny bit h away from x and draw a chord from A to B. So if you move h along the x-axis, it's meant to be really tiny amount. Over here, you have moved to point B. The coordinates, x-coordinate of point B will be x plus h. Now the y-coordinate of point B will be f of x plus h in general. And the x-coordinate of point A is x, and the y-coordinate is f of x. Then the gradient of the chord, so let's call it gradient of the chord AB, is simply, if you look at that, let me just draw this triangle in different color. It's going to be the difference in y, so the y-coordinate of point B minus the y-coordinate of point A, and the difference in x, so the x-coordinate of point B minus the x-coordinate of point A. So effectively, what you're going to obtain here is f of x plus h minus f of x, so the difference in y, and then difference in x is simply that h. There you go. Now imagine that h getting smaller and smaller, so closer you are moving that point B closer and closer to point A. And then the gradient of that chord, or the line that joins A with B, will become closer and closer to the gradient of the curve at point A. And this is the idea of actually finding the limiting value of this expression as h tends to 0. So this is the definition of the gradient function. So it's limit, which is the limiting value. So as h tends to 0, so the gap between the points A and B is going to be diminishing. You're going to find the limiting value of that expression. Okay, so you did it last year, so we're going to extend this idea into finding the derivatives of some trig functions from first principles. So here where the small angle approximations come into play, you need to know these and you need to be able to use them. So sine x for small values of x, this is why the small angle approximations can be approximately equal to x, provided you're working in radians. You can try it on the calculator. If you're not sure, let's say, what is sine of 0.1? It's something that rounds up to 0.1. What is sine of 0.05? There you go. That will be pretty much 0.05 if you round it to 3 significant figures. So it's correct to 3 significant figures. So that's the first result which you need to be able to quote at any time. I think this is in the formula booklet. Cos x for small values of x approximately is equal to 1 minus a half of x squared. So if you think about visually, if you think about graphs, if you were to sketch sine x and the line y equals x for very small values of x, as I've done over here, the closer you get to the origin, so as for x is really small, that line will pretty much overlap the graph y equals sine x. Now similarly, if you were to sketch y equals cos x and then y equals 1 minus a half of x squared, so I've sketched the 1 minus a half x squared in red and the cos x in black, you could see that for values close to 0, the graphs will pretty much overlap. So that's why it is approximately equal to. Now, you can actually think of these results in rearranged form. So if you have, formally, we'll put a limiting value of sine h as h tends to 0 is equal to h. So that's the same result, but written more mathematically with the limits here. And with the second one, if you imagine dividing that x through here, you'll be getting 1 on the right hand side. So you can also work out the limiting value of sine h over h as h tends to 0. So that is going to be limiting value of h over h, which is 1. The same here, you can write it in terms of limiting values as h tends to 0. And then you can imagine dividing throughout this expression throughout by x. Over here, you can have cos h. If you cos h minus 1, this can be replaced with minus a half of h squared, and then over h cancels, and you're left with limiting value of minus a half of h. Well, if you replace h with 0, because it tends to values very small, close to 0, the answer is going to be 0. So we're going to have a look at some examples. So the first example over here is going to be proof from first principles that the derivative of sine x is indeed cos x. And we are assuming that as h tends to 0, sine h over h tends to 1, and cos h minus 1 over h tends to 0. So let's have a go. So you look in the formula booklet if you don't, if you need reminding of the formula from the first principle. So there's the formula. Here is our function. So if we allow f of x to be equal to sine x, then f dash of x, I'm going to use this formula with my f of x being equal to sine x. So the first one, wherever I've got f, I'll put sine. This is going to be sine of x plus h minus sine of x over h. Okay, so let's keep on writing that LIM, so limiting value, as we go along. So what we can do over here, we can use the addition formula to expand the sine x plus h. So let's replace it. Remember, it's sine x cos h plus cos x sine h minus sine x over h. So what I'm planning to do, I want to be able to use these results as I've been warned to do in the question. So in terms of, in case of cos h minus 1 over h, so what I want to do here is look for cos h. I've got cos h here. But how do I get minus 1? Well, this cos h is multiplied by sine x, and here I've got minus sine x. If I factorize that sine x, I will obtain cos h minus 1, and then I'll still put cos x sine h, and that's over h. Now I'm going to separate these two. Keep on writing limits in front of this fraction, and here I've got cos h minus 1 over h multiplied by sine x plus sine h over h. So the terms involving h, put them together, multiplied by cos x. There you go. So now let's look at our expressions. I have got cos h minus 1 over here, divided by h, and I've got sine h over h. Just appeared naturally without thinking. So this one here can tend to 0 as h tends to 0, and sine h over h tends to 1 as h tends to 0. So let me carry on this side here. So you are going to get actually, once you've replaced it with 0, you don't need to, so we got rid of h's, you don't need to put the limiting you've already considered when h tends to 0. So the next line of working just need to be written 0 times sine x plus 1 times cos x, which is clearly cos x. There you go. So you could say over here, I mean, you can copy because cos minus 1 over h is equal to 0, and limits of h tending to 0, sine h over h is equal to 1. But it's pretty obvious that we've been asked to use these results. Okay, so let's look at the next stage. Okay, so we can do the same thing in arriving at proving the result for cos x. I'm not going to do it, but you might want to practice it because it could be asked in the exam. So sine x, if this is my y, differentiates to cos x. Now cos x differentiates to minus sine x. Now if you've got a multiple angle, then it will go to so kx, it will go to k cos kx when you differentiate sine kx. If you differentiate cos kx, it will go to minus k sine kx, and remember to multiply by k. Now you might want to remember those results by applying like a circle. So sine differentiates to cos, then cos differentiates to minus sine, and then minus sine goes to minus cos, and then minus cos goes to sine. So we are differentiating this way, and then people like to do it because then they use the reverse of the circle anticlockwise to find integrals. So integrating this way. So opposite, so 12 o'clock is S, 6 o'clock is minus S, 3 o'clock is C, 9 o'clock is minus C. So it's easy to remember. Okay, so let's have a look at example 2. We've got to find dy dx of the following three functions. So we're just going to apply those results. So sine goes to cos, sine kx goes to k sine kx. So dy dx here is simply 2 cos 2x. And it's 2 in front because you've got 2 in front of x as the angle. This one, cos goes to minus. So dy dx, it's going to be a minus answer. Minus, and you'll have 5 sine 5x. And over here, you can differentiate the sum. So 3 cos x, that will go to minus 3 sine x. And then you've got 2 lots of 4, so it's plus 2 times 4 cos 4x. So let's just tidy up the second term, and you're going to get 8 cos 4x as the second term. So minus 3 sine x plus 8 cos 4x. Okay, in the example 3, we are going to use the derivative of this function to find the stationary point between 0 and pi. So we need to differentiate. Stationary point means dy dx is equal to 0. So it tells us to differentiate. So dy dx, differentiate a half of x, that goes to a half. And cos 2x goes to minus 2 sine 2x. So that means a half plus 2 sine 2x is equal to 0. So that gives me sine 2x is equal to minus a quarter. So we are looking for all the solutions between 0 and pi. 2x must be between 0 and 2 pi. And remember, we are dealing with radians, so we're going to do sine inverse of minus a quarter. So sine inverse of minus 0.25. So this gives me minus 0.25268 radians. Now let's find the other solutions. So if you remember, for the sine graph, there you go. If this is my minus 0.25, so this one here is going to be pi plus 0.25, and this one here is going to be 2 pi minus 0.25. So I'll do the second one first because it's easier. 2 pi plus my answer, that gives me 6.0305, and then the second one is going to be let me just times that by minus 1. Apologize. So it's 2. I've done that one. Let's do find it first. There you go. Okay, so let's do pi minus ans. Okay, 3.394. to 7. Okay, so I kept all these. Now I need to divide by 2. So divide by 2. So it's 1.6971. And the second one, 6.0305. Divide that by 2. That gives me 3.01525. So let's round our answers to 3 significant figures. X is equal to 1. This one will go to 70, or x is equal to 3.02. Now it asks us to need for both stationary points. We found x coordinates so far, so let's find the y coordinates that correspond to this one. So the y coordinate, let's go with this one. First, I just need to substitute 3.02 into our function. So 0.5 times ans minus cos 2 times ans. So this one here is 0.539. And this one over here, let me just step back to our value. It was 9427, divide that by 2. So let's sub it into the function 0.5 times ans minus cos 2 times ans. I wouldn't round the answer, reuse the rounded answers, just use more accuracy, at least one more degree of accuracy to find the y coordinates. So that's what I went even further than that. So 8, 2. So this is example 3. This is the second point, and this is the first point. Make sure you pair up the coordinates, or either like this or like this. So don't just randomly put x's and y's in separate places without making certain that you've shown which x goes with which y. Okay, so we're going to move on to, no, this is it. You've got to move on to exercise 9a.